This is chemical equilibria in Gibbs free energy part 3. I'd like to show you an example of how we can apply the relationship of Gibbs free energy to equilibria. Let's imagine a relatively simple reaction involving the use of adenosine triphosphate to phosphorylate glycerol. This would be catalyzed by a kinase, and the product would be glycerol 3-phosphate plus adenosine diphosphate. So let me draw out what we're looking at. Imagine we have glycerol and ATP, and ATP then phosphorylates this, so we end up with, excuse me for overwriting here, this molecule. So we have, that's a phosphate, so we have glycerol 3-phosphate. That would be the product. This reaction is reversible. We can look at a table to find the standard free energy change for ATP, the hydrolysis of ATP. So ATP plus water is going to be react not to completion but quite far, ATP plus phosphate. And the free energy change of this from a standard table is 30.5 kilojoules per mole. Likewise, we can look up in a table the hydrolysis of glycerol 3-phosphate plus water to create glycerol plus a free phosphate. The free energy of this hydrolysis is equal to 9.2 kilojoules per mole. The reaction we're looking at is equivalent to the hydrolysis of ATP and the formation of glycerol 3-phosphate. So we can subtract these two values to see what the delta G would be. So the delta G of this reaction, that's standard delta G, at standard conditions, will be equal to, excuse me, I forgot the negative signs here. So that's a favorable downhill, negative 30.5 and negative 9.2 will be negative 30.5 subtract, because so this reaction ATP going to ADP, that's the direction we're looking, and glycerol going to glycerol 3-phosphate is the other direction, so we have a subtracting a negative value 9.2, and this is equal to 21.3 kilojoule per mole. So that is true of this reaction up here. Let's resume, and I can look at these values. I can use these values now. So we know the change in free energy of this reaction in the direction drawn, right? This direction drawn is 21.3 kilojoules per mole. So I can use some standard relationship that the change in Gibbs free energy for the reaction in non-standard conditions is going to be equal to its standard Gibbs free energy change plus RT natural log of the reaction quotient, where the reaction quotient is going to be equal to the value of the products divided by the value of the product of the products divided by the product of the reactants. So that's glycerol 3-phosphate and ADP divided by the product of glycerol, which I will use to say G, and ATP. So we can use this value to figure out what this quotient will be. So what I'm asking then is, at equilibrium, what is this number going to be? R is universal gas constant, T is temperature in Kelvin. So let's set this up. Delta G at equilibrium is equal to 0. Therefore, delta G at standard conditions is going to be equal to negative RT ln Q. And we want to find what Q is. We want to find at equilibrium what is the value of Q, knowing that the change in free energy of this reaction is 21. So we can add that here, 20, and I'm sorry, I keep on forgetting the negative sign. So negative 21.3 is going to be equal to negative 0.008315 times 300 Kelvin about ln Q. I want to know what Q is, so first let me move these terms to the other side. So essentially what I'm doing is I'm taking this equation and I'm going to move the negative RT to the other side, so this equals log Q, and then I will raise each of these as an exponent to E, so that leads to, I'm going to put that up here, getting a little bit busy here, Q is equal to E to the power of negative delta G naught, standard conditions, RT. So this value here, so let's put in the values here. So I want to know what Q is. Q is going to be equal to E to the negative 21.3, but sorry, that's a negative value anyway, divided by 0.008315. This is in kilojoules. Notice that I'm using, in this case, I'm using R is equal to 0.008315 kilojoules per mole. If I'm calculating in joules, I'd better use it times 1,000 times 300. And what I end up with here, the calculator, if I do that part, I'm going to end up with a positive value of about 8.54, and that's equal to Q of 5109. That's approximate. So let's round it up to 5100. What does that mean? That means that because the ATP donating as phosphate to glycerol is so favorable, that the free energy change of negative 21.3 kilojoules per mole translates at equilibrium to a reaction quotient that this concentration of the two products times themselves. So the product of the concentration of these two is 5,100 times more than that. That's all.